So, let us now look at microstructure of a hypereutectoid steel. Hypereutectoid means the alloy composition is greater than 0.8 weight percent carbon. So, it is on the right hand side of this 0.8% carbon, which was the eutectoid steel. So, let us take a vertical line denoting that composition. So, this line represents our hypereutectoid steel. We saw in the evolution of hypoeutectoid steel that austenite first became alpha plus gamma, which means ferrite first formed, and that ferrite we call hypoeutectoid ferrite, and then the remaining austenite transformed to pearlite alpha plus Fe3C. Identical situation happens here with the hypereutectoid steel, only the first phase to form before eutectoid reaction is now Fe3C cementite and not ferrite. So, you get pro-eutectoid cementite and then you get pearlite. So, that is the only difference. So, here also at a higher temperature you will have, in the single phase field you will have austenite, polycrystalline austenite, with grains and grain boundaries. But then when you enter this alpha gamma plus Fe3C region, you will start having Fe3C forming. So, at a temperature somewhere there, you have gamma, now the amount of gamma which will form, first of all remember that the Fe3C which forms starts forming on the grain boundaries. So, you will have grain boundaries where Fe3C will first form. So, here you have, this is original austenite and this is Fe3C which is forming. Also, and then you can finally here also the austenite phase which is there, the composition will evolve and it will again evolve towards, the composition will evolve towards this eutectoid composition. So, when you will be close to the eutectoid horizontal, when we are reaching close to the eutectoid horizontal, the remaining gamma will be at the eutectoid composition and at eutectoid temperature. So, it will transform as you know now. So, below the eutectoid horizontal, if we try to draw the microstructure, so you have these austenite boundaries. I am drawing it in dashed line because I want to cover these with the Fe3C. So, Fe3C has formed along these boundaries. Depending upon the amount of Fe3C, which will also depend on the composition. So, lots of Fe3C will form I am assuming that there is composition is such that there is sufficient Fe3C to form along all grain boundaries. So, you will have a grain boundary network of Fe3C, but this Fe3C now using the same nomenclature will now be called proeutectoid cementite. Or Fe3C, and the remaining austenite will form into perlite. So, you will have perlite forming, whatever austenite was left at 725 degree on cooling will transform into mixture of alpha and Fe3C. So, that is perlite. If you look at the amount here again, you can calculate the amount of proeutectoid cementite in the alloy, and that will be of proeutectoid. I am just writing pro Fe3C in short, the proeutectoid Fe3C. So, you will again use a tie line above the eutectoid horizontal, the red tie line which I have drawn. So, if you have composition C naught, Fe3C is now on the right hand side of this diagram. So, the left arm is representing the Fe3C fraction. So, the Fe3C fraction will be C naught minus 0.8 divided by 6.67 minus 0.8. And generally in steel, even in the hypereutectoid steel, it is greater than 0.8, but it is not much greater than 0.8. So, it goes up to 1.2. Steels greater than 1.2% carbon generally will become too brittle. So, most engineering alloys will engineering steels will have up to maybe 1.2% steel, even if they are hypereutectoid. So, the numerator is much smaller. You can see numerator will be if C naught is equal to, let us say 1, for 1% let us calculate. So, this will be 0.2 divided by 5.87, 0.2 divided by 5.87, which will be a much smaller number. So, the fraction of cementite which will come out will not be too much. So, that is why, and they initially come on the grain boundary. So, they appear to be as a network covering the grain boundaries. So, with this we complete the microstructure of steels.